Okay, we were gonna next justify this formula for how the pressure changes with depth in a fluid, and the context here is that this container is at the surface of the Earth, so we're, in a location where little g is 9.8 meters per second squared, and the idea is, yes, the pressure is non-zero up here. There's atmospheric pressure around us, but then it starts increasing as we go down in the fluid. And here's the relationship. It's the density of the fluid times little g times the distance h that you've gone down in the fluid. That tells us the difference. This also applies even if you're going from somewhere down to further down. It tells you the change in pressure as you go down by a distance 8. Okay? And that change in pressure is just the fact that you've got the weight of the fluid above you when you're further down. There's more fluid above you the further down you go, and that causes a greater pressure down there. In this diagram, imagining an aquarium or something like that here, if we take this rectangular cube of water, which has area A, top and bottom, and it's a height h, I'm just going to draw that as a cube over here for a free body diagram. And it's got several forces on them. One of them is the weight force on it. So the weight force is mg, and we're going to write the mass in that case as rho times the volume. Rho of the fluid times the volume, and the volume is A times H, right? It's the cross-sectional area times the length of it. So rho Gh8. That's not necessarily an obvious formula until you think of it that way. So there's also fluid pressure, right? On each of the 6 sides, the fluid is drumming against. This side is drumming against the left-hand side. Now, the left-hand side and the right-hand side are going to sort of balance each other out because however hard the fluid is bouncing off the sides here, it's bouncing it the same way over here. Same thing with the front and back. Because when they're at the same depth, there's the same mass of fluid above it. So the left and right and the front and back forces sort of cancel out, and so I'm not going to draw them on here. I'm only going to draw the top and the bottom forces, right? The fluid is pushing down on the top and it's pushing up on the bottom. Let's start with the top. The force from the fluid above there is equal to the pressure at the upper surface times the area A, right? And the pressure on the force on the lower surface. Remember, pressure is force times area, so to get a force, we multiply by an area. The force on the bottom is the pressure at depth h times the area A of the bottom. Okay, and those are all the forces that are on it. Well, there are other forces that cancel each other out on the left and right and front and back surfaces. I just didn't draw those on here for economy's sake. Okay, so in order to apply F net equals ma, I'm going to choose a plus y direction to be up because all these forces I've drawn are vertical. And then let's do the sum of the force y components equals 0 because we're assuming this fluid is in static equilibrium. Even if it's moving a little bit, the formula I gave earlier is going to be approximately true, but it does change a little bit if the fluid's moving. So we're imagining a static fluid here. Some of the forces on this cube of fluid have to be 0 because it's not moving. Let's add all 3 of those up. So the P depth h times a comes in with a plus sign, the other 2 come in with minus signs. And what I'm just going to do is solve for P at depth h. First thing I'll do is divide by a there. Pressure at depth h is equal to the pressure at the surface plus rho Gh. And therefore, the change in pressure between the depth h and at the surface is just going to be rho Gh. That's what this formula says. If you go down a distance h in a fluid, the pressure increases by rho Gh. If you go up by some distance h, then we would consider that h to be negative in that case, and we would have a negative change in pressure from lower to upper positions. All right. Now, one thing that we're going to need to keep in mind is that tells us about the change in pressure, but we already had some pressure up at the surface by virtue of the fact that we're underneath a tremendous atmosphere. So what's the pressure of the atmosphere around us at sea level. So again, I'm going to go back to this picture where we've got the differing densities and also differing pressures as we go down, right? As we go down, there's more and more atmosphere on top of us until we get a maximum pressure at the bottom because we got a whole lot of stuff pushing down on us there. So what we want to find out is what is atmospheric pressure at sea level in pascals. And we can't use that formula that we just derived, the rho GH, in this case, starting at the top and going down, because we assume that the density is constant in that particular derivation over there. So that rho GH formula is only going to be valid if the density of the fluid is constant over the entire height h that you're changing it. And here, if I'm going to go from the top of the atmosphere down, that's certainly not true. So since rho is not constant, I can't calculate it that way, but we can measure it with a pressure gauge. And so we find out that at sea level, when we measure it, the average pressure, pressure goes up and down a little bit with the weather, but the average pressure, 1.013 times 10 to the 5th newtons per square meter, or pascals. And a lot of times, I think in the book writes it as 101.3 kilopascals. So that's atmospheric pressure at the surface of the Earth on average. That's the SI units. You'll also see it written in non-SI units that by definition, that number at the surface is called 1 atmosphere. So an atmosphere is a non-SI unit for pressure, but it's very convenient because I always know at the surface of the Earth, the average pressure is 1 atmosphere. So another inconvenient fact is that I talked about measuring this with the pressure gauge. Now, most pressure gauges, like the one you use to pump up your bike tires and know the proper pressure to pump up your car tires, those don't measure absolute pressure or real pressure. They measure what's called gauge pressure. Gauge pressure means something different. The gauge pressure means how much is your pressure above atmospheric pressure. Okay, so in other words, if your bicycle tire gauge is sitting here and nothing's being inflated, it reads 0. Now that doesn't mean that the pressure is 0 around us. The pressure is 101.3 kilopascals. But if it's just measuring how much above normal atmospheric pressure the pressure is on it. So in order to get the absolute pressure or the pressure, if you measure the gauge pressure, you've got to add on the atmospheric pressure at the surface of the Earth to get the true pressure. So you also have to be careful whether someone's talking about gauge pressure or just plain old pressure. So, for example, here we've got the old cylinder with the pressure increasing as it goes down. So these are the pressure or the absolute pressure as a function of position inside the cylinder. Similarly, the gauge pressure is 0 up here, and then the gauge pressure starts to increase as it goes down. So in other words, it's at atmospheric pressure up here until we get the fluid, and then as we start going down, it's a little bit above atmospheric pressure, more above it, and so on, according to the formula delta P equals rho GH. All right, so let's do a very simple example having to do with the pressure increase at a faucet. So here's a situation you see in many towns where they've got the water tower up at a certain height, so a bunch of water up here. There's a pipe that comes down, and in this simple example, it's just put right into your faucet, but it's essentially the same way. That pipe's being split off and going to lots of faucets. And we want to know, yes, of course, at the surface of the water up here, assuming it's open to the atmosphere, the pressure is atmospheric pressure, which is being labeled as P0 here. What is the increase in pressure, or the difference in pressure, between atmospheric pressure and down at the faucet if the distance from the top of the fluid down to the faucet is 30 meters? So in other words, if we start up here and we go down, 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 and up a little bit, we've gone down overall by 30 meters in getting there. So to calculate that, the change in pressure is the pressure at the faucet minus the pressure at the surface. And according to the formula we just derived, in this case, the water's density, water is what's, I guess I should have put a slide in about this and I didn't put it in, but water is pretty incompressible under most circumstances that you're going to find on Earth. the density of water as you go down in the ocean, from the top of the ocean down to the deepest trenches, the density of the water does not increase that much. The pressure isn't able to squeeze the water because the water molecules are already pretty packed in close to each other, so it just can't be compressed that much. And so the density of the water is pretty much constant all the way through. And so that ρGH formula that's only true for incompressible fluids or fluids that have constant densities, it's pretty much true there. So the difference in those pressures is equal to ρ of water times G times H, and that means the pressure at the faucet is equal to atmospheric pressure plus ρ of water is 1,000 SI units in SI units, little g is 9.8, and H is 30 meters, how far we went down. So if you put all that in together, that's 3.95 kilopascals, or 395,000 pascals. All right, let's work on a problem now. Here is something I've seen for sale for aquaria before, so that you've got two aquaria and you want your fish to be able to swim from one to the other. What you can do is build a little bridge, which is an inverted U-tube that upside down with both sides in it, and then you have to pump the air out of there so that it's filled with water, and there's no way for air to get back in. And the fish can swim around and swim up over here and then go over there. There's some questions about pressure here. So when we do that, what's the pressure at the bottom of the aquarium? In other words, down here. And here I'm asking about pressure, not gauge pressure. What's the pressure at the very top of the water bridge tube? So you need to use the distances that are given here. What's the gauge pressure at the very top of the water bridge tube? So take a break, think about answering those questions, and we'll continue on with the solutions.